vector space theorem on basis statement. Let V be a n-dimensional vector space and set S is equal to V1 bar, V2 bar, Vr bar be linearly independent linearly independent set in V, then set S can be extended set can be extended to a basis S dash is equal to V1 V2 V1 bar V2 bar Vr bar Vr plus 1 bar Vn bar of V. So what is given here? Given dimension of vector space V is equal to n and S is equal to V1 bar V2 bar Vr bar be any linearly independent set in vector space V. And what is our claim here? Our claim is that, and we want to show that the set S can be extended to a basis set S dash is equal to V1 bar V2 bar Vr bar Vr plus 1 bar Vn bar, vector bar Vn bar. Okay, so this is our claim. Now proof. Now I am going to take one example to before start the proof of this theorem. So consider one example here. Say, okay, so consider here, suppose we take V is equal to R cube and take S is equal to, say S is equal to 1 0 0 0 1 0 B is linearly independent set in R square in V. Okay, so now we want to extend this set. Now since it is linearly independent, but it is not a basis set, okay, because it contains less than n vectors. What is dimension of V here? Dimension of V, which is equal to dimension of R cube, which is equal to what? 3. So we want to extend this set to a basis set. So if we consider any vector which does not lie from this set, yes, suppose we consider here vector V bar which is equal to 1 2 3, which does not belongs to set S, okay, then we form a new set S dash which is equal to 1 0 0 0 1 0 and 0 1 0 and 1 2 3. Then this set S dash is what? This set S dash is basis for R cube or vector space. So this what we want to do here. So we are going to select a vector which is outside from the set S. So same logic we are going to use here. Okay, same logic we are going to use here. So proof. Now if first case, if R is equal to n, then S is n, then S itself a basis, then there is nothing to prove if r is equal to n. Now if r is less than n, then choose vr plus 1 bar from set v minus s, that is which does not belongs to s. That is what is the meaning this? Vr plus 1 bar belongs to v, but vr plus 1 bar does not belongs in set yes. So if we select this vr plus 1 bar, then we select this vr plus 1 bar such that set s1 is equal to v1 bar, then set v1 bar, new we form a new set v2 bar, vr bar, and vr plus 1 bar is linearly independent set in v. Now if r plus 1 is equal to n, then s dash is equal to s1 basis for v. Okay, and that is we extend to a basis set what? Yes. Okay, but if r plus 1 is less than n, then again we use the same procedure. We select vr plus 2 bar, which is belongs to v minus s, such that this new set s2 is equal to v1 bar, say v1 bar, v2 bar, vr bar, vr plus 1 bar, vr plus 2 bar basis is linearly independent set in v. Again, and if r plus 2 is equal to n, then s dash is equal to, we select s dash is equal to s2 basis for v. Now if suppose okay, again if r plus 2 is less than n, again instead of suppose, not suppose, if r plus 2 is less than n, then we continue this process, till set s is extended to a basis s dash is equal to v1 bar, v2 bar, vr bar, vr plus 1 bar dot vn bar. Okay, and hence the proof, and therefore proof. Here we have proved this theorem. So the proof is very simple. Like in this example, the dimension of v is what? 3, and it contains only 2 vectors. So we select a vector which is outside from this set S, or which does not belongs to here v bar does not belongs to S, but v bar belongs to what? R cube. That is what this implies. That is 1, 2, 3 is a vector belongs to v minus set S, and therefore we form a new set. Now here the set S dash contain exactly 3 vector, and dimension of S v is what? Also 3, and therefore this new set S dash is a basis for R cube. We use the same logic to prove that, or to make a new set S dash which is extension from set S, and which is what? A basis for v.